Thank you for the introduction. Thank you to the organizers for the opportunity to speak, especially virtually. I really would have liked to be there in person, but it didn't work out. I'm glad to at least join you virtually. Okay, so to begin, just to say a little bit about the setup here, I'm really starting in a similar place to Lon's talk a couple hours ago. But I'm looking at a triple of data that I'll call just Bartnik data, or sometimes it's called Bartnik boundary data. And what this is sigma is just a surface. It's topologically S2. Gamma is a Riemannian metric on the surface. And then H is just some function, some non-negative function here. And we can take all this data to be smooth. Okay, so we've got this Bartnik data. We're also going to have a manifold M, a smooth manifold. It'll just topologically be R3 minus a ball. So it's got a spherical inner boundary. And then we're going to have G as representing an asymptotically flat Riemannian metric. Okay, so this is three-dimensional. I won't write down the decay conditions and everything, but it's all standard. The idea is that G is going to the Euclidean metric at infinity at some specified rate. Okay. Oh, and I'm going to use R throughout this to represent the scalar curvature. Okay, so that's the setup. One definition we'll use throughout the talk is that we'll think of Mg, the Riemannian manifold, as an extension of the Bartnik data, the given Bartnik data. If, and apologies, we've seen similar definitions like this already today a couple times, but the idea is if the boundary with its metric, the induced metric is isometric to sigma with its Riemannian metric gamma. Okay, so that's what we mean. The metrics patch together. The extension is called admissible. And admissible if the scalar curvature of G is non-negative, and if there's a condition on the mean curvature of the boundary. Specifically, if this given function H is pointwise bigger than or equal to the mean curvature of the boundary pointing into the manifold. So H partial M here, this is the boundary mean curvature. If you wanted to, you could consider equality here. But in general, this inequality on the mean curvatures corresponds to positive scalar curvature in a distributional sense along the boundary. The picture to have in mind here is maybe something like this. So this will represent the Bartnik data. So that's some spherical data. It's often the case, not always, but it's often the case that this data comes from the boundary of some compact free manifold, omega, that may have non-negative scalar curvature itself. But that could be the induced mean curvature from that. And then this extension would be something you could glue to it to get a asymptotically flat manifold. Like that. Okay, so that data there is what's going to go throughout this setup. There's part two of the talk, 2 parts of the talk. The first one's just called minimizing mass. That'll be the shorter one. I'm just going to review some things that are known. So minimizing mass, this will correspond to a discussion of Bartnik's quasi-local mass. So the idea here proposed by Bartnik back in the 80s is essentially to seek, one way of thinking of it is to seek an optimal admissible extension. Some extension that's somehow geometrically optimal. The point of view he was taking is that optimal here would mean the least possible mass. So the definition that this leads to, the Bartnik mass of Bartnik data, M sub B, you're just trying to minimize the mass. It's the infimum of the ADM mass of Mg such that Mg is an admissible extension. Okay. If you leave the definition like this, it actually turns out not to be a very good definition. So there's one other condition you have to put in. I'll put in, I'll just call it generically condition star. It won't be particularly relevant for the kinds of stuff I'm talking about today, but basically the point of star is that this condition needs to rule out a certain kind of behavior that was originally identified by Bartnik. You could have extensions that they're sometimes called like a bag of gold example, but you could have a very small neck here, some tiny minimal surface, and then maybe your sigma is down here. You don't want to allow situations like this because you can make the mass arbitrarily negative, even keeping non-negative scalar curvature. Sorry, you can make it arbitrarily small, close to zero. So without some condition, maybe no minimal surfaces enclosing the boundary, or the boundary has to be outward minimizing. Without something like that, the infimum would just be zero. Okay, so we have some condition like this. Now the Bartnik mass, I'm not going to write down everything that's known about it. One of the first things to learn about it is it's actually very hard to compute exactly. It's really only known in very specialized cases such as rotational symmetry. So it can be challenging to work with. There are many estimates for it from above and some from below. Bartnik identified a number of nice properties it has as a quasi-local mass in general relativity. I'm going to focus on a couple specific properties in terms of what's known about minimizers. In general, it's not known what hypotheses you can put on your Bartnik data to ensure that minimizers in this infimum actually exist. But some things are known about generic properties of minimizers. So one thing that's known, for example, is that any minimizer in this definition of Bartnik mass must be static. And then this is mentioned earlier in Lon's very nice talk, for example, but I'll just review here what I mean. I'm phrasing it in a slightly different way, but static for me here means there exists a solution, a non-trivial solution U to this equation here. LG by itself without the star is the linearized scalar curvature operator at the metric G. LG star is its formal adjoint. Specifically what it is, if you write it out, is there's it's a tensor, there's a Hessian term with respect to G, a metric term, and a Ricci curvature term. So it's saying that has to be zero. If you're in the asymptotically flat setting, then it turns out the scalar curvature has to be zero as well. It's known the scalar curvature has to be constant, and in asymptotically flat, that's only possible if the scalar curvature is zero. Okay, so by the way, that also, scalar curvature zero here is equivalent to U being harmonic. So sometimes you'll see that written down as part of the static equations. Okay, this was first shown a couple decades ago by Corvino. This is a localized argument. It produces some non-trivial solution. It doesn't really say anything about the asymptotics or the global behavior of the function U. And more recent work with Mike Anderson, we were able to show that U has nice behavior, positivity under hypotheses, and approaching 1 at infinity. Okay, and then this leads to studying static vacuum metrics in their own right. That's not the direction I'm going to go in today, but that's one source of studying static metrics. Another thing I want to focus on, because it'll have an analogy in the second part of the talk, is just a general property about the ADM mass as a function on metrics. it's that the ADM mass behaves favorably for minimizing. So if you think of it as a functional on metrics, what I mean here is essentially that it's semi-continuous in the right way. That's really the minimum that you would want to be true if you're trying to minimize it. So this is lower semi-continuous. This in some sense is like a reality check to see if Bartnick's problem makes sense. So just to say a few words about this without writing out full theorems, these are results, including some with Dan Lee. Roughly, that range of years there. But essentially what the idea is saying here, roughly, is that if GI goes to G. So if this could be Riemannian metrics, they actually could be more general objects. But to start off, let's just say if you have metrics that are converging, they're asymptotically flat, assume non-negative scalar curvature, then you actually get the ADM mass of the limit is bounded above by the limits. This is really this is what the direction you get for lower semi-continuity. Okay. So you get a statement like this. Of course, it matters what topology you're talking about for the metrics. The first case, that was the solo work that was for local C2 or pointed C2 convergence. The work with Dan Lee was for C0 convergence that was substantially more involved. And then also the latest work was for Sermani and Wenger intrinsic flat convergence. Okay, so these are, you can think of as a series of results telling you that the mass behaves the way you would want it to for minimizing. Okay, so that was the first part of the talk. That was the quicker one. In the second part of the talk, the bulk of it, I'll talk about a complementary problem. It's kind of, in some sense, you could think of it as a dual problem. This is on maximizing the capacity. The goal here is really to study, it's a new Bartnick-like optimization problem. So everything here is very much inspired by Bartnick's program. And one thing I should say about this is very much work in progress, maybe even I would say work in relatively early stages here. So just keep that in mind. But I thought in the spirit of this being a workshop, that would be an okay thing to still talk about. This is going to be about capacity. We've definitely heard a bit about capacity, for example, in Pengzi's very nice talk earlier today. But I just want to say a few things. Let me remind you of the definition. So definition, if we have one of these asymptotically flat metrics on an M, actually, no, not the capacity of M, capacity of the boundary, this is a normalizing factor, and then you're looking at an infimum of the Dirichlet energy. So you try to minimize the Dirichlet energy among test functions on the manifold such that phi on the inner boundary is 0, and then phi goes to 1 at infinity. So you're trying to interpolate between 0 at the boundary, 1 at infinity, in really the most efficient way possible in this sense. So that's the capacity. You can find a minimizer, a unique minimizer that's the harmonic function with these boundary values that can be useful for computing the capacity. Since capacity is going to play a crucial role in the rest of the talk, I do want to spend a little bit of time just giving some intuition for what it's doing. So this can be helpful for thinking about capacity. First observation is just what is capacity in Euclidean space for balls. That's really the simplest case I could imagine trying to understand. If M is R3 minus a ball of some radius, so this is a round ball, and it's with, let's say if the metric G is just the Euclidean metric, then the capacity of the boundary in dimension 3, the capacity of a round ball is just the radius of the ball. Okay, so it's giving some notion of the size of a set. You could think of it like that. What else? The capacity is monotone. So it's monotone increasing. Basically, if you have a surface and then you have a surface enclosing it, the enclosing one will have generally larger capacity. So it's getting bigger as you go out. Another thing that's useful to think about is some situations where the capacity is really forced to be small. And I'll think of this as long or narrow necks. They're sometimes called long or narrow necks. Diminish the capacity or imply small capacity. So what do I mean by this? A long neck, this was alluded to in Pengzi's talk as well, but if you have some asymptotic flat manifold and you have like a long cylindrical neck like this, and let's say you have a cylindrical neck of length L, the idea is that the capacity of the boundary would go to 0 as the neck gets longer and longer. And you can see that just by using test functions that are interpolating linearly over the long neck. Okay, so it's something that's getting buried deep down a well. Will have very small capacity. Similarly, if the neck isn't necessarily long, but if you have a very narrow neck, like that earlier example with the Bartnik mass, and you've got some region in here, but you've got this small neck. In this case, the capacity of the boundary would be very small. You can see that by just imagining that your test functions just go through all of its transition from 0 to 1 in the area where the metric's small in the neck. So you can get small capacity from that too. Okay, actually a couple other quick things to help understand the capacity. One of them is that the capacity is insensitive to wells. So what I mean by that is if you have some extension of some Bartnik boundary data, you're going to have some capacity there. If instead you take that and you cut out a little ball, cut out some small ball, and you glue in like sometimes it's called a gravity well, or like gluing in a finger like that, not something enclosing the boundary, but something off to the side. This is not going to have a big impact on the capacity. The capacity kind of is blind to perturbations like this. Okay. And then finally, one last thing about capacity. So in some ways, capacity is, there's a lot of similarities between the capacity and the mass. One thing is that really makes them different. Well, many things make them different too, but one thing I'll point out that's useful in some of the later arguments is that capacity, I was going to say global, maybe non-local is a better way of saying it. The ADM mass only cares about what's happening at infinity. It's a flux integral at infinity. Capacity, if you change the metric on any set, it's generally going to change the capacity just by the nature of the way it's defined. Okay. Now there's many known connections between capacity and scalar curvature and mass. We saw a lot of those earlier in Pengzi's talk and references to other ones, so I won't review all that here, but there's a lot of reasons that these are all interconnected with each other. Okay, so the problem I'm going to look at studying, you can kind of guess what it's going to say from the title here. The problem is to try to optimize the capacity of extensions. If you have some Bartnik data, you want to try to see if you can find an optimal way of arranging an extension from the point of view of capacity. Now, if you think about this quickly, you realize that because of the kinds of examples I was mentioning about wells and necks, you don't want to minimize the capacity. If there's anything that's going to be happening here, you're going to be maximizing it. So that's really what you could hope for there. And also, if you start playing around with extensions, playing around with some examples here, you realize that the maximum is going to be infinity unless you have some additional requirements. So specifically, to have a shot of having something meaningful here, non-negative scalar curvature is important, and also that inequality on the boundary mean curvatures. So in other words, we're really just going to be looking at the admissible extensions, or else this would not be very interesting. Okay, so the definition proposed here is this functional. I'll just call it a script C for capacity. It's defined on a triple of Bartnik data. And it's very much the analog of the Bartnik mass. It's a supremum of the capacity of the boundary with respect to that metric, such that G is an admissible extension. So that's the definition. Notice if you compare that with the Bartnik mass, there's one very obvious difference besides the fact you're maximizing instead of minimizing. There's no condition star here. So there's no need to put in some kind of condition star requiring, you not to have minimal surfaces enclosing it, or having your boundary being outer minimizing, because the kinds of examples that make that a problem for mass are actually not optimal for capacity. If you had like a small minimal neck around your surface, that's going to make the capacity small, not big. So one reason this might be easier to work with than the Bartnik mass is you don't have a condition like that to worry about. Another way of thinking about what this is doing is, again, it's trying to seek the most optimal way of getting from your boundary out to infinity with non-negative scalar curvature. You're trying to arrange things as efficiently as possible from the point of view of capacity. Okay, so it's also kind of, you can think of it as like a max and min problem, because the capacity is defined as an infimum, and then we're taking a supremum of that. Okay, so first of all, a couple things are in order just to make sure this isn't a completely trivial thing to be talking about. So just a couple basic facts. The first one is, there's two ways I want to show this is non-trivial. The first one has to do with, you want to make sure, just like with Bartnik mass, you want to make sure you're not taking n for a sub over an empty set. So extensions exist. If, in many cases, if, for example, if you have positive Gauss curvature, or more generally, if you have the lowest eigenvalue of this this operator minus Laplacian plus Gauss curvature on the surface, if that's positive, this follows immediately from the Mantelidis chain construction. The idea is they construct admissible extensions in this case. So that's going to have some positive capacity. So therefore, the maximal capacity will be positive. So this is really just assuring you that in many cases, extensions do exist. Second thing, on the flip side, you want to make sure that the capacity function is not infinity. So it is actually finite. The proof of this, it's easy to see given known results. It really follows immediately from a result of Bray and Miao from 2008. Hungzi mentioned this result in his talk. This uses Huskian and Ilmanen inverse mean curvature flow, but they give an upper bound on the capacity that only depends on the Bartnik data. So basically, using this, you can show that it's not just finite, you can give an explicit bound here. So it's this area of the boundary over 16 pi term, 1 plus, and then a little more energy term Okay, so you can show something like that. So you have this explicit upper bound. Again, this all requires non-negative scalar curvature. Okay, so just like with the Bartnik mass, you look at this definition, and one of the first questions you'd want to ask is there an optimizer? In this case, is the supremum actually achieved? So that's really one of the guiding questions here, just like it is for the Bartnik mass. Is the supremum achieved? And I don't know the answer to that in general. In a special case, you can comment on this. If you've got round Bartnik data, so you have a round sphere with a constant mean curvature metric on it, the answer is yes. And your optimizer is just Schwarzschild. Basically, you get equality in Bray and Miao's inequality there. So these extensions are just rotationally symmetric exterior regions in Schwarzschild. Okay, so those actually achieve the supremum. In general, just like for the Bartnik mass, I want to say what kinds of things could you say about these maximizers in general. So results, first one's really just an observation, just a short lemma. And it is that maximal capacity extension. So by this, I mean, one of these metrics that achieves the supremum in the definition. Maximal capacity extensions are scalar flat. So they have identically zero scalar curvature. Okay. This is similar to a result for the Bartnik mass where those minimizers have to be scalar flat as well. The way you see this is a little bit different. Again, just due to the way capacity is defined, it's you can make use of the fact here that it's a non-local definition in a way that doesn't quite work for the mass. But if you did have positive scalar curvature somewhere, you'd have it somewhere in the interior. What you could do is zoom in on a region where you have strictly positive scalar curvature, and you can locally increase the metric pointwise. You can locally raise the metric. You can do this conformally, for example, on a small set. Now, if you do that with a small enough bump to the metric, you can still preserve positive scalar curvature. And if you do this, if you increase a metric, you actually raise the capacity. You can strictly raise the capacity, so that would contradict that you started with a maximizer to begin with. So it's telling us that if you are looking for these maximal capacity extensions, the place to look is scalar flat metrics. Okay, what else? You can say more than that, just like you can for the Bartnik mass. There's a variational description of these maximal capacity extensions. So this theorem here is that if you have a maximal extension, if G maximizes this functional here for given Bartnik data, then there's something, it's not the static vacuum equations, but it's something similar. So if it maximizes this, then there exists a solution, a non-trivial solution U. Oops, non-trivial. To this system of equations. It's LG star U, so it still involves the formal adjoint of the linearized scalar curvature. And it's really like that equation, but it has this inhomogeneous term on the right-hand side. There's this term minus d phi tensor d phi plus a half grad phi squared times the metric. What's phi here? Phi is the capacitary potential. So phi is the harmonic function that is 0 on the boundary and 1 at infinity. Okay. So if you want to look for maximizers, this PDE is what you'll be studying here. So again, it's like the static equation, but there's this additional term involving this harmonic function. To say a few words about how the proof of this goes. The first thing to try is to, I think, try to mimic Corvino's argument, where you do a local deformation to the scalar curvature and argue if that can be done, then you couldn't actually be at a maximizer. That doesn't quite work here, at least in any kind of obvious way, because if you're going to bump up the scalar curvature locally, the capacity could behave in an unpredictable way. The mass is very predictable because the mass only cares about what's happening out at infinity. But if you bump up the metric to change the scalar curvature, you could be changing the capacity in who knows what way. So you really need something else here for this to work. So first calculation, you want to do the L2 gradient of the capacity functional. So think of that as a functional on metrics. That L2 gradient ends up just being that right-hand side of the equation there. So you calculate that, and then the rest of it is very much following the way we approach this with Anderson, which was following a program due to Bartnik, but it's really a constrained optimization problem. So it's a Lagrange multiplier. The reason it's a Lagrange multiplier argument is you can be thinking of this as having an optimization of capacity with the constraint of scalar flat metrics. Okay, so that's your constraint set, because you know if you have a maximizer, it has to live on that constraint set by the first observation. Okay, if you play around with that, then what pops out is the Lagrange multiplier ends up producing a non-trivial solution U to that equation. Okay, let's see. Oh, let me give an example. We know Schwarzschild, for example, rotationally symmetric Schwarzschild should give these maximal extensions. Special case of that would be R3 minus, say, a ball of radius R naught. That should be a maximal capacity extension, and that works out. You can easily find the static potential. That's just a rotationally symmetric harmonic function. And then you need some potential U that's the solution to this. You can find a radial solution to that pretty easily. The U that you get is could have any constant in it. The constant corresponds to the homogeneous solution. The constants there are in the kernel of LG star, and then minus a term R naught squared over 8R squared. If you want, you can choose that constant to be 1 so that U goes to 1 at infinity there. So that's what the solution U looks like in the Euclidean case. You can also write it down explicitly in Schwarzschild as well. Okay, so got that example. One direction I want to suggest going with this is that this equation here, I'll call it equation, I already used star for something, I'll use, I don't know, how about a cross or something there, or a dagger, whatever you want to call it. Dagger there may be interesting to study on its own, even separated from this problem. And not just necessarily in this global asymptotically flat case, it could be interesting to study when phi is just any harmonic function. Okay, not necessarily a capacitary potential. So in that case, you could ask, what can you say about the geometry of metrics that admit a solution for some harmonic function phi and some potential function U? So one thing you can say about them, proposition here is if GU is a pair that solves that equation there, let's say non-trivially, U is not 0 here, then, and this is for any harmonic function phi, then in that case, G, R sub G, the scalar curvature, is constant. So that's a property these solutions actually share with static metrics. Static metrics have to have constant scalar curvature, and that's also the case with this here. I've got enough time here. Let me just go through the proof of this. It's a short, but I think a little bit fun argument for why these have to have constant scalar curvature. What you do, similar to dealing with static metrics, is you take the divergence of that equation there. So you got your equation there, you take the divergence. What that leads to is that u times the derivative of scalar curvature has to be 0. Okay, so what's going on there is that if the scalar curvature is not constant, by the way, I'm assuming, of course, m is connected here for this to work out. So in that case, u is 0 on this open set where the scalar curvature is non-zero derivative. So u equals 0 on that side. Okay. If u is 0, then LG star u is 0. So then the right-hand side is 0 on that open set. So d phi tensor d phi minus that plus this 0 on some open set. If that open set's empty, of course, we're done. But if it's non-empty, then you can look at the rank of both of these tensors here. This is a multiple of the metric, so it has full rank or 0 rank. This term right here has rank 1 or 0, so rank at most 1. So the only way you can have those adding up to 0 is if the rank argument implies that both of those tensors are 0. So that implies phi is constant. Not globally necessarily, but on an open set. Okay. But then phi is a harmonic function. So then it is actually it's constant on open set, so it's constant globally. So phi equals constant on m globally. So if phi is constant, well then the whole right-hand side is 0, and then you're back to having a static metric. So you're back in that case. So then LG star u equals 0, and then you can use known results to get that r equals constant. Okay, so just a short little back and forth there between u and phi. Okay, let's see, maybe I'll skip over a little bit here, just in the interest of time. Let me now go back to a question or a point I made about minimizing mass. You could ask a corresponding question for maximizing the capacity. Is there some theoretical or analytical basis for maximizing the capacity, just like the question was asked for minimizing the mass? So you're maximizing here. So what you really want is the capacity to be upper semi-continuous. So the question is if GI goes to G, is it true that the capacity at the limit is bigger than or equal to the lim sup of the capacities? Okay, that's the direction you'd want things to go if you're maximizing. Okay. So a couple things. One, this is easy to show if you do for C0 loc, this is just an exercise. It's just playing around with the definition of capacity. That is much easier than the corresponding C0 result that I mentioned earlier for lower semi-continuity of mass. For capacity here, that's much easier. But you might want to ask about weaker convergence, because that's what you would expect in these types of optimization problems, just some kind of weak convergence to a limit. So what about this Sermani-Wenger intrinsic flat convergence? So I'll just take just a couple minutes to mention a theorem. This is more recent joint work with Raquel, who's speaking tomorrow, and Jim Portuguese. But basically what we have is a sequence of spaces converging. These don't have to be, they could be Riemannian manifolds. They don't have to be manifolds. They could be these more general objects called local integral current spaces, which are the things that show up in intrinsic flat convergence. But if you have these converging in a pointed VF is intrinsic flat convergence with volume preserving. Okay. And I'm going to be a little vague here, but I'm going to say let Ki, a subset of Mi, correspond. There's a way to make this precise, but I'll just say let it correspond to K, a subset of M. Ki and K are compact here. Then you get the capacity going the way you'd want it to. So capacity measured in M of K bigger than or equal to lim sup of the capacities, Mi of K. To give one example of corresponding regions, they could all be balls of the same radius centered around converging points. Okay. By the way, one of the reasons I focused on, we have focused on intrinsic flat convergence is just because of the promise it has shown for dealing with some of these convergence problems in general relativity where you have a lower bound on scalar curvature. Okay, with the time left, I just want to maybe say a little bit about open questions. Honestly, at this point, I have a lot more questions than I have answers. Let me just share, maybe I'll take just one, maybe I'll list one question that I think is important for understanding. This is one of many. I've said a Euclidean ball complement is one of these optimal maximal capacity extensions, but it's not so clear if you have R3 minus some other domain that's not necessarily a ball. So is this a maximal capacity extension where, I mean, even to start, if it helped, you could just say this is, you know, convex. Maybe more generally, it could be mean convex and star-shaped or something. But if you have some general region in R3, you look at the Bartnik data, you want to ask, is that an optimal extension? And I think either way here, the answer is going to be interesting because if it's if the answer is no, then there's some other more efficient configuration than Euclidean space, which I think would be interesting. And if the answer is yes, I'm not sure about the techniques that would get you to that point that would characterize this this case sharply, but I think that would be interesting too. There's a number of other open problems, but maybe I'll just, with just the last minute or so, I'll just end on just kind of some of the big picture about why I'm interested in this problem. For one, it's kind of a parallel to the Bartnik minimal mass problem. So it's possible this could give some new insights into that. Particularly, there's some senses in which this problem should be easier than the Bartnik minimal mass problem. I mean, maybe that's not saying much because that problem itself is so challenging. But for example, you don't need that condition star to rule out minimal surfaces and small necks, so that's a favorable thing. You might have better control on mass minimizing, or sorry, on capacity maximizing sequences than you would on minimal mass extension and minimal mass sequences. For example, you shouldn't have those long cylindrical necks forming. That's a similar point to what Pengzi was saying at the end of his talk. Another thing, and this is very much inspired by Pengzi's results from earlier, is it might also be interesting to look at the ratio of mass over capacity and see if that's something worth optimizing. That's kind of a union of the two halves to the talk. You could minimize mass, you could maximize capacity, or it might look, might be a little bit easier to look at the ratio there and see if you could optimize that. Okay, I think I will stop there. Thank you so much for your attention.
Thank you for your talk. Are there questions?